Okay, so this section is going to be the properties of waves. So we're going to talk about all the properties and then how to solve for those using the algebra. So the first main property is just going to be amplitude. Amplitude's a pretty basic measurement of a wave, so there's nothing to really solve except for actually measuring. So amplitude is the height of the wave, and it represents the energy carried. So the height of the wave, the higher it is, the more energy it has. So you've probably seen seismograph readings where they have, a big seismograph, and the higher it goes, the more energy or the stronger that earthquake would have been. I like to say rest to crest when we're measuring. So I'm going to do it up here real quick. If I were to make a wave, and I'll just do a transverse wave here, and I was going to have my rest point in the middle, the amplitude is going to be from the rest point to the top of the wave, which we call the crest. That's a measurement. It's going to be the height or a distance of how tall the wave is, and you could also do it from rest to trough, but it doesn't rhyme, so we like rest to crest. And you just make a measurement. So there is a unit for amplitude, and the unit is just going to be what we measure distance in, or meters. So anytime you're measuring the amplitude, you're going to report that data in meters. Okay, the second thing is going to be the wavelength. And the wavelength is just what it sounds. It's the length of a single wave. So length is also a unit that's measured in meters because it is a distance. And when we did our virtual lab, you were using meters as your measurement. And again, remember the symbol is lambda, the Greek letter, and the meaning is going to be the distance of one wave. So I like to measure that crest to crest. So I'll put that in parentheses. So we measure from the top of one crest to the top of the second crest. That's the easy way to do it. Or you can do the distance between two identical points on consecutive waves. So if we're looking at something that has to do with wavelength, I'm going to use the crest to crest thing. And if I had a wave, I would just go make a point on each crest, and the wavelength is going to be that distance between the two. So that I'm going to use the lambda sign for that. Okay, so that's going to be our wavelength we'd measure. Okay, you can also measure any other points as long as you do the same point on consecutive waves. So if you didn't have two crests in the image, you could do a midpoint as long as you did that same midpoint on the next wave. Or you could go trough to trough, but notice there's not a second trough, so you could pick a different point. So anytime you do a same point on two consecutive waves, you have a wavelength that you can measure. So this is going to be in a transverse wave, how you would do it. Crest to crest. But what if we have a longitudinal wave? So sometimes if we have a longitudinal, it's going to be the distance between two wave pulses. So we're going to say the contractions, when you notice that they contract. And I will kind of draw one out like I did on the last notes, where you have where it gets compressed, or compressions, I guess you could say. And another one. So the wavelength on a longitudinal wave, you could do it at any point as long as it's the same point on the two compressions. So you could go from start to start, you can go from end to end, or middle to middle, as long as it's the same point. So I'm going to go from the start of this wave, and I'm going to draw a line to the start of the second wave pulse, and that would be the wavelength on a longitudinal wave. Okay, as long as it's the same point on two consecutive waves. So we know we measure that in meters. We know we measure amplitude meters. Both of these are lengths or distances. Okay, so now we're going to get a little more into what we have to calculate. So we're going to talk about frequency. So frequency is, the definition is the number of wave cycles per second. So that's a really basic definition, number of wave cycles per second. So I like to think of it as, if you drew kind of a timeline here, and you said, I'm going to do this twice. Both of these spaces are going to represent 1 second of time. So I'm going to get them as close to the same length as possible. So we're going to represent this as 1 second of time here. And this is also 1 second of time here. So the frequency is the number of wave cycles per second. So you might notice that sometimes a wave, my pencil breaks all the time, a wave is going to have several wave cycles per 1 second, and sometimes it may be not very many in comparison. Okay, so in this case, which is going to have a higher frequency? So the higher frequency would be a higher number of wave cycles per 1 second. So this one has several, this one has much less as in terms of how many per second. So we would say the first box has a higher frequency, while the second box has a lower frequency. And let's relate this to wavelength. If we were to measure the wavelength in the first box, the higher the frequency, the shorter the wavelength. Where here we have a lower frequency, but the wavelength just got much longer. Okay, so that's how they relate. And remember, I talked to you in the lab and asked you, and they should be inversely proportional. So if one goes up, frequency, then wavelength would go down. Or vice versa, if frequency goes down, wavelength goes up. Okay, so there is an equation that we're going to do with this. So equation is going to be F for frequency. So frequency equals the number of cycles divided by time. So T is time. So frequency is the number of cycles. There's not really a unit for the number of cycles, wave cycles. That's just a number represented. So we don't really have a unit for that. But we do have a unit for time. We know that time's unit is in seconds. And we also know that frequency from our lab is in hertz. Okay? So hertz, spelled like that, is what we measure the unit of frequency, hertz. So that is going to be the number of cycles per unit of time, or seconds is what we use time in. Okay, so there is a circle if you have to use it. So number of cycles is on top. Frequency and time are on bottom. So if I was going to look for the time, I'd cover it up and I'd do the number of cycles divided by the frequency. If I was going to look for the number of cycles, I'd cover it up and I'd do frequency multiplied by time. And that would give me all of the different ways to rearrange that. Okay, so another property we're going to do is called period. So period is also a time. So if you talk about a time period or a period of time, that's the same in waves. And so since it is a time, it is going to be the time it takes to complete one full wave cycle. So the time it takes to complete one full wave cycle. So it's different than frequency. It's sort of the opposite there. So this is how many waves in a second of time, and this is how much time it takes to complete one wave cycle. So in the frequency drawing up here, one wave cycle would be 2 consecutive points. So if I started here and came back to here, that's one wave cycle. That's going to be a small number of time compared to the full second of time. So it's going to be much less than a second to complete one wave cycle. So a high frequency will have a shorter period. Now this one, it took a much longer of that second to complete one wave cycle. So when you have a lower frequency, you're going to have a higher or a longer period of time. Okay? So there is the equation that we're going to use here. And the equation is just going to be, instead of saying period, we know it's a time. So it's going to be time in seconds, remember, is going to be equal to 1 over frequency. And remember, frequency is in hertz. So we're taking that second of time and dividing it by the frequency. So we're taking the time, the second of time, and we're dividing it by how many wave cycles go through. And that is going to give us the period or the time period for one wave cycle. Okay? So if you were to take any of those frequencies, and let's say the frequency was 8 hertz, you would do 1 over 8 or 1 divided by 8, and that would give us the amount of time it took to get one wave cycle. Okay? All right, the next one is going to be wave speed, and we're going to have 2 ways to get wave speed. So since speed is technically the same thing as a speed or velocity that we learned earlier in the year, anytime we were trying to get speed or velocity, we knew that speed was a distance over time. It was how far something traveled in so much time. So in this case, this is going to be the distance a wave travels per unit of time. And in this case, we mostly use meters per second, but sometimes you could change that if you were using a larger scale. So the first equation will just be the speed of the wave equals distance divided by time. So distance is meters, time is in seconds, and speed would be in a meters per second. So sometimes they'll say, oh, this wave travels this far in this much time, what's the speed? Well, that's how you do it. And then we would use the circle for this one as distance on top, speed, and time on bottom. Okay? So we could solve for any of those. The second equation is speed equals frequency times wavelength. So speed equals frequency times wavelength. The circle here would be speed on top, frequency and wavelength on bottom.